All right, good morning, everyone. I'm there from Dubot. Welcome to our training today. You can hear me and see my screen now, right? Okay, today we are going to introduce you a little bit of our core function, introduction of our CR robots. And now we will begin. Okay, first I'm going to introduce you about some features about CR collaborative robots. First, the CR robot comes with 6-axis design, and this material is a little bit old, but it says there's 4 models, but there are six different models for different needs and applications. What's new is the CR3L and the CR7, CR12. There will be 7 different models, and we have the different 7 different models with different payload design for your different applications. Also, we have the safe skin technology that makes CR series to be the safest cobots for man-machine collaboration. So with the safe skin, we can guarantee you the safety and efficiency at the same time. Also, after unboxing the robot, you can set up in 20 minutes and 1 hour to go. Put into application, and it supports extensive protocol of the end arm tooling. Also, it shows wide range of applications and tests with great weight and requirements such as palletizing and handling. So we can have these different models with the weight starting from 16.5 kilograms to 40 kilograms, with the payload starting from 3 kilograms to 16 kilograms, and the max reach from 440 to, I think the latest one should be 1500 mm for the CR3L, and with the repeatability starting from 0.02 millimeter to 0.03 millimeters. Okay, so this is a whole picture of our industrial line products, starting from the MG400 with a payload of 0.5 kilograms, and then the M1 Pro, the payload 1.5 kilograms. Then is the CR series. I'm going to use a pen to show you where I'm talking about. So for this one, the CR3L, CR7, and CR12. Those 3 models are the latest model we recently launched in this year. So those are the new models covering different payload. The CR3L, the difference between CR3L and CR3 is the reach of the robot. You can see that the reach of CR3L comes to 1700 mm. So it comes with the same payload of CR3, but with a much higher reach. You know, just for CR3, you can reach a range of just 220 mm. And with CR3L, the cover would be 1700 mm. And the CR5, CR5, those are the original models. And the CR7 and CR12 are also the new models. And now CR16 is our is the maximum payload model in our current range of our products. So with the different models, you can choose the best model that suits your project best. And by the way, during our training today, if you have any question, feel free to ask us during the chat function of Zoom meeting. You can input a question here, and our engineer will help you to answer your questions. Also, there will be a Q&A at the end of the training. There you can also talk to me, and we will answer your questions at the end of the training. Okay, during the training, you can type in your questions there, and our engineer will help you to answer. All right. So we just talk about the different payload of different models. Also, I'd like to mention the repeatability of different models. You can see starting with the desktop MG400, repeatability is plus or minus 0.05 mm. And for M1 Pro, it comes to 0.02. And for the rest, 0.02 mm. This is a very, very good repeatability accuracy. But for the CR3L, the repeatability is increased a little larger from 2 to 5, because the range of the arm is much longer than the others. So with a longer arm, the repeatability decreased a little bit. So it's changing from 2 to 5. And for CR10, CR12, and CR16, the repeatability increased from 0.02 mm to 0.03. Even on this level, is also the top of this kind of robots in the industrial, you can see. And the maximum speed of TCP starts from 2 meters per second to 4 meters per second. Yeah. So there are different features for the CR robots. And first is the plug and play. It's easy to use, and you can really set up and use it into real application. You can even use the handheld teach. You can use the trajectory recording function to do very simple tests, even without some device like a smartphone, tablets, or your PC. You can do just with the robot itself. With the buttons on the end of the robot arm, we can record the trajectory and teach the robot to do something. Also, all the industrial line products supports graphics programming. You can use the blocks to write your own program. So this makes it easy for the beginners who are new to this kind of industry. So it's easy to begin, and later you can use the script for complex projects as well. And also, it comes with drag and drop teaching, which I mentioned with the buttons on the robotic arm. You can use easily with the handheld, and use the hand teaching and the drop function to record the trajectory and repeat the trajectory. Also, it comes with intelligent interaction, which we will introduce you later, and it comes with multiple level security. And this is what we think most for these collaborative robots. This is increase both the safety design as well as the efficiency in the collaborative robots. Also, we support different types, models of editors. So we have a rich robot ecosystem for you to choose. And also we have diversity application packages. We are developing some, and there will be more coming out that way. All right. So those are some pictures, shows you the features of the robotic arm. The first one is safe. You can see with the safe skin, the robot can sense the human body before it touches the robot. The robot will stop when before it's touching the human body. So with this feature, the robot arm will not do any harm to the human body who's working along with the robot. The second feature is easy to use. You can see that we are using the end buttons. We are using the end buttons on the robot. We use the buttons to teach the robot to do something. And then when the teaching is done, just play the button, and the robot will do the same routine as we teach it. So these features are suitable for some basic applications that you don't want to do it with your programming software, and we can do it with the buttons. We don't need the tablets, we don't need the PC, we don't need the smartphone. We can just do it with the buttons. It's easy to get your hands on it. All right. Third one is intelligent. You can see we can cooperate. We can work with different other sensors along to do some application. For the third one, you can see the picture above is the camera, is the robot working with camera to pick out something, and the second one would be the robot to to do a polishing. The second picture here, the picture downside is that a robot working together with a force touch sensor. This guarantees you the robot delivers the stable force on the surface of the item is going to polish. So this is a 3D vision deep learning force control adapting technology. So we are working with different factors. The fourth one is precise. You can see we can do it with very high performance motion control with the 4-parameter collaboration technology. So the motion picture optical control can guarantee a very smooth using experience. And fourth is open for different other development, such as the secondary development support. So you can use some other protocols such as TCP/IP, SDK, something like that, to develop your own programs without our control software. You can do it with your own. Okay. We are now suppose 11 software programs, and it's compatible with more than 20 development performance platforms. So this is a little introduction of the safe skin. You can see that we are offering that different options when you order the robot. One with the safe skin and one without the safe skin. This is what the safe skin. It's very soft. It's a new kind of silicone material, and it's soft. And so this guarantees you the safety when you touch it. And it comes with compact design. You don't have to worry about the room of the robot safe skin. It's just on the surface of the end of the robotic arm, and there will be a 360-degree protection for all directions. And also, it supports different different material detection, such as metal, plastic, human body, clothes, wood, something like that. It can sense different materials. And the safe skin can guarantee the pre-collection sensing technology with the 15 centimeter percentage distance, and it will stop or avoid obstacles before collection with a 10 milliseconds response sensitivity. With this safe skin, we can increase the efficiency and safety at the same time. The human-machine collaboration speed increased from 0.25 meter per second to 1 meter per second. So this encourages the efficiency and the safety at the same time. Also, it's easy to use. You can see that those are our robots. They can set up in 20 minutes, and with the application done, we can do it in 1 hour to start the application. For the platforms, we support Android, iOS, Windows. We support those different platforms to use. Also, if you want, we also have a teaching pendant for you to choose. This is our teaching pendant. But usually, if you don't have any requirement for it, you can just do it with your tablets or your PC. We have the app for the Android and iOS, which you can download easily on your tablets, which is much easier to use wirelessly. Okay, we can also do with the hand-guided learning, such as this one. We can teach the robots for some points with the handheld, and also we can use the graphic programming, just as shown in the picture here. We can drag blocks together to write your own program. It's very friendly for the new users of the robots. Also, you can see we have this and buttons in here. There will be smart interactive panel, and you can use buttons very easily to do the drag and drop teaching. All right. So those are some applications we work with the other sensors. You can check them one by one. The first one would be voice recognition. With the processor of the computer, the robot can detect what the human says and then do the right commands. The second one would be the force control, as I introduced a little bit before. So yeah. And this is a vision system. We are using the camera to do the application with the visual AI system. So this is our high precision 4-parameter DH composition technology. The absolute positioning accuracy. Aaron, this is something that is different from the accuracy I told before. The accuracy before is called repetitive accuracy. This is the absolute positioning accuracy. So this is the 4-parameter DH composition technology. We can provide the absolute accuracy from 0.2 to 0.4 millimeter control. Okay. So just finishing the introduction of CR robots, here's what we are going to share during our training today. The first one would be PTP motion. Second would be stack transporting. Third one would be complex tracking motion, and fourth one will be remote boot up with the appendix on the end of the training today. Okay. Okay, the first one I'd like to introduce you about is the PTP motion, and let's check for this video. All right, I don't know why this video cannot be played anymore, but okay, no worries. Just listen to me, and I will introduce to you. So if we want to learn the programming of CR robots, the adjusting motion speed of the robots will be what you need, and the use of simple motion instruction of CR, the use of program flow control instructions, and the operation of our interface, and all by the analysis of the PTP motion cases. Okay, so in the part of PTP motion, we have different tests for our training. First one would be to creating the program. Then we need to optimize the running speed of the program. And third one is we learn to use the motion commands. And the fourth one would be to control the program flow. The fifth one would be I/O monitoring, the interface operation. We will introduce you them one by one. Okay, the use of the program with the CR robot is quite easy forward and straightforward, and here's it. So the programming flow is quite easy. We just start with the latest software we call the Doable Studio Pro. Create a project, start project. Then we teach the points. We can use the hand guide function to guide the robot to reach somewhere. And if the points you need it very accurate, you can move the robot with your hand, and then you can control the robot with the panels. With the panels in here, in the control panels, to do it, to do a more accurate move with the buttons. All right. With the handhold, we can guide the robot with the big moves, and then for the manual fiction, we can use the buttons. And then with the points ready, we can read the program, and then we can call the points in our program, and then we can debug the program, check if there's anything wrong. If there's not anything wrong, we can run the program. Okay. So usually for project of CR robots, it usually consists of 3 different parts. The first one would be the saved points information, which is the coordinates information of the different points. This is the first one. And the second one would be the global variables. If you are using the variables, it's necessary to check before you run the program. And the last one would be the scraps or the blockly project files. So you can see that we are dividing the SRC into different threads. The first one is called SRC0. It's the first thread. We can run at most 5 of them from starting SRC0 to SRC4. So there are 5 threads in total. But be advised that all the motion commands must be in thread 1. Motion must be included in SRC1. So for the others, you can put it into the other threads, but for motion commands, you have to write it in thread 1. Okay, so let's continue. So for the motions, there will be different commands and different parameters. So first, I'm going to introduce the parameters here. The first one would be speed, or speed S. This is a speed, linear speed with a proportion motion speed value range from 1 to 100. The bigger the number is, the higher the speed is. The second one would be the accelerators or acceler. This is acceleration speed. Sorry. The value starts also from 1 to 100. The higher the value is, the higher the acceleration is. The last one would be the CP, smooth transition. What is CP? CP is the smooth transition during the motion. The range is from 0 to 100. There will be picture on the afterwards, and I can show you about the difference between. I can show you the function of the CP as well. So there are some notes that you need to be noted, that if you don't set up the parameters for the speed S, acceler S, if they are not set in the program, the default value is 50, which is the middle of the level. Users can increase the bit by setting up the parameters to increase to reduce the cycle time of your project. You can increase the speed as well. And what are the difference for speed and speed S, acceler and acceler S? So the difference is that speed and acceler are suitable for go, move G, go R, move JR, and speed S and acceler S are suitable for move, jump, arc 3, circle 3, move R for the different commands. So actually they are of the same function, but just for different commands. You can choose the corresponding one to your commands. Okay, so you can here see this picture is. I think I can put it larger. Okay, so you can see from here we are putting these different meters in here. Before the forever block is joint speed ratio 100, joint acceleration 100, continuous path ratio 100. This is the CP. CP is short for continuous path. This is the CP, and this is the CP ratio 100. Okay. Let's continue. So a little more introduction for the acceleration. The acceleration of the speed. That means if the acceleration is higher, the change of the speed is much faster. And jerk it means it's actually the changing speed of acceleration. You can regard it as the acceleration of acceleration. So it's a little tricky, but it's that meaning. All right. So the higher the jerk is, the faster the acceleration changes, and the higher the acceleration is, the higher the speed changes. So we can go to the settings for the different jog settings and change the different accelerations there, but please don't change it to a very large speed. If you have any problems, means changing of the parameters, you can come to us and ask for support. We will provide you with advice there. And the motion speed of the robot is the combination of joint speed, global speed, joint speed, and speed in the parameter, and with the global rate. So you can see if the program runs slow, you should change from 3 different aspects. First one would be the joint speed, then the whole speed in the script, and the global rate. Global rate is what we put in here. This is the global speed. Okay, we can choose the different global speed during the whole progress. So you can see when running, if the motion speed is lower than preset, it's mainly due to the running distance of the machine, and speed does not reach to the set speed. So users can increase the speed by adjusting the speed and acceleration. It's not recommended to modify the speed parameters. So if you have any requirements that you want to increase the speed, try with this one. Try with this speed in the joints, like I mentioned here, the accelerations, the speeds, something like that. But usually we don't encourage our users to change these parameters by themselves. It will cause problems sometimes. If you need to change, if the speed or the global rate, this is also you can do. This is what you can do, and this is what you can do. But if you want to change this, you can contact us first, and we will provide you with some suggestions for you. Okay. All right. These are the motion commands. We can see that this is the difference between the move-J or go and move commands. You can see the biggest difference is that the trajectory. The trajectory for move-J and go would be a curved line. The robot will go from A to B in a curved line, which is suitable, which the algorithm thinks is most suitable for the robot. But with move command, it just go from A to B in a straight line. So if your application requires the robots to go in a straight line, use the move command. But for others, you are recommended to use the move J and go. You can choose the different ones according to different applications. So below here is some examples for the use of the commands. This is the go command, and this is the parameters there. We put 100 speed, 100 acceleration, and CPU 100. And this is move J. Move J means the move of the joints. And here also move. This is speed 100, acceleration, CPU 100 as well. So we can say we can combine the different commands with the different parameters in there. And now this is what I'm talking about for the CP. You can see the difference between those two different scripts. The biggest difference, the only difference is that the first one comes with a TCP 100 and the second one doesn't. So what's the difference? Those pictures are the trajectory of the robot moving from P1 to P3. P1, P2, P3. And this one same, P1, P2, P3. You can see that we use these commands, the robot moves starts from P1, directly P2, then go to P3 directly. But with this one, you can see that the robot, in reality, the robot does not reach to P2. It just come close to P2, but it will not choose to, it will not reach to P2. So this is what the CP do. This CP will provide you smooth transition from one point to another. So in a sentence like this, if we start from P1 and the final point is P3, and when you see P100, the robot will move close to P2, approaching to it, but it will not really reach to P2. So you can see from the picture to know the use of CP. With the CP commands, we can smooth the motions of the robots. So which will make the robots move in a smoother way, and it's more fast. Okay. Wait a moment here. Sorry, we will continue. So this is the function of CP. So if you don't want the robot to go too smoothly, you can decrease the value a little bit. You don't have to put 100 in there. Okay. So after running the script, the yellow cursor on the host computer indexes the script runs, but this function is not async. Okay, I think I will just escape these parts because, okay. You can we all know that there will be two different programs in the when you run program. Is that the running of the scripts and the running of the robots. So most of the time, the running of the robot and the running of the scripts are not at the same time, which means in our previous controlling software, which is called Doobot SS Studio, there will be a yellow cursor on the host computer index the script runs, and the yellow cursor index the robot runs. You can see that if you used our SS Studio, you will see that the two different cursors are not running at the same time. In most cases, the two are out of sync. So usually the script will run ahead of the robot for most cases. For example, if we use this scripts, the move P1 first move to the grabbing position, DO1 turn on to collect the object, wait 100 milliseconds, hold still for 100 milliseconds, and then move P2 and left, and we do detect if the robot is if the object is in position. So after this script running, you will find the returning value is always 0. Why is this? This is because when you run this script, this value will be returned immediately after the script is running, before the robot can take the object to the distance P2. So when the value is returned, the robot itself is not reaching to D2. It's on the way, but it's not reaching there. Okay. So how do we prevent this kind of situation from happening? This is the reason. The reason of this question is the two running is not in the sync, which means the script and the robot itself is not running in the same time. So how do we stop this? So we are using this syncing here. Sync. We are using this function, which means we need to wait until those commands are finished together, and then we return the value at the end. So with this function, the script waits for the robot to reach to P2 and then returns the value of DI1. So in this way, there will be the right value returning after the robot moves to P2. Okay, so this is the usage of this is the use of sync. All right. And wait, we put the wait and sleep in the same page because some of our users are often confused when they use two different commands, which they look very familiar. So what's the difference between wait and sleep? Wait is actually the delay of the algorithm query. Executing wait will move a delayed command into the algorithm execution query. It's generally used to delay the motion and I/O operations. So we can see that wait is more likely to use on the moments of the robots. For example, in this one, move P2, move to the grabbing position and DO1 to grab the robot. Wait 100. It means hold. Hold means the moment. We hold the moment for 100 milliseconds, and then we do the next move. So wait is actually for the movement. And sleep is the interval between two commands, but the running interval cannot be guaranteed. It's generally used to delay the programming. So you can see that sleep is more likely to use for scripts. So we can use the sleep for different scripts. We run the scripts from move to do to do. We can use wait. We can use sleep. Sorry, we can use sleep in here to put the interruption between the two commands. So this is what we use with the wait and sleep. So you can just remember the features that wait is for movement, sleep is for script. So that's the biggest difference. Okay, so for the programming language, it goes with CR is Lua, which is fully supports Lua native functions, APIs, multi-threading, and other mechanisms. I'm not going to introduce a lot of Lua in here, but you can check more details in this page here. So yeah, just I'm going to introduce you a little main features of the Lua looping here. So we have this while loop, for loop, repeat until loop, different kinds of loop types. So for different conditions, for while loop, when the precondition is true, the program will be told to execute some statements repeatedly. So checks whether the condition is true before executing the statement. This is what the while loop do. And for loop executes the specified statements repeatedly. The number of repetitions can be adjusted in the for loop commands. And repeat until means repeat the loop until specified condition is true. So this is the difference between the different loops. I believe this is universal for different kinds of programming language. So this is very universal. Yeah. And how do we to jump out of the loop? We can use break statement to accept the current loop or statement and start to execute the following scripts. And here's the if statement. If statement consists of a Boolean expression as a conditional judgment, followed by other statements. And also we have the if-else statement. If statement can go the else statement to execute the else statement command, while if condition operation is false. So if it's true, just go to condition 1. If it's not, if it's false, go to the next one. Okay. If nested statements, we can use one or more if else statements within one if and if else statements. Okay. And here I'm going to introduce you about I/O status and DO signal manually through the DO monitor interface. This is the I/O monitor in the software of our DoBot Studio Pro. Okay, as most of our users are here and like to introduce about our DoBot Studio Pro. Some of our old users might be familiar with DoBot SA Studio, but now we are no longer we are encouraging our users to converting the programming software to DoBot Studio Pro. This is our latest software, and there will be a lot of new functions on this software. So if you have no problem changing your projects, you can totally try this DoBot SA Studio DoBot Studio Pro with your project. But in some running projects that are already finished, you can use your current software as well. The DO signal, the DI signal can also be simulated during the program debugging. So usually we can use this panel to test. So we can use this one, for example, while true do, if DI1 is on, then move, else print hello world, and then sleep 100. So this program can be executed by simulating DI signal. You can actually try this program on your own if you have a robot around you, and this training material will be sent to you later. Another thing that about the collision detection function, this is included in almost in all our CR robots. So as I mentioned before, the safe skin is optional. You can choose one CR robot with or without safe skin. Of course, the price will be different, but this one is in default that is available for every CR robots. So we can choose to change the level of the collision detection. If this function is turned on, the robot will immediately stop when it runs into an obstacle to avoid dangerous collision. So we have we have 5 different levels of the collision detection. The higher the level is, the higher the sensitive is. For example, if we use the level 1, it might be punch the robot for once and the robot will stop. But with level 5, the robot might slightly touches you and it stops. So the higher the level is, the less force will be triggered the collision detection function. So, but for some other applications that there's no one working around the robot, and you don't want the robot to run in the collaborative mode, you can also disable this function. They have this button here. You can also disable it to reach a higher working speed. But usually, it's open in default, and we suggest our users to keep this function on. All right. Okay, this is the second part of the stack and transporting. There should be a video here, but I'm not afraid that the video cannot be played. I'm not sure. Oh, it's okay. Okay, so this is a demo of our distributors and who's using our CR10 for palletizing. And I'm going to introduce you about the palletizing here. So in the part of stack transporting or palletizing, there will be 4 tests. First one is getting familiar with Doobot Plus plugin. Second is programming of simple stack transporting. Third one would be programming of complex stack transporting. The fourth one would be the applications of stack process. Okay, so we just saw what is palletizing, and now we're going to do for the preparation. To use the palletizing, we will use the indicators, or we call it. So for the CR robots, the standard we use is this ISO 9409/50/4/M6 standard. This is a universal standard that is suitable for most of collaborative robots. So this is how the standard is. You can see we have the diagrams in different angles. We can see that this is the flange that is suitable for the CR robots. We can use this to find the most compatible indicators. And how do we communicate between the indicators and the robot? So we have this. We have prepared the I/O and RS-485 communication ports on the end of the robotic arm. You can see there should be a buckle on the end of the robotic arm. I'm going to show you later, and it supports I/O and RS-485 communication. Those are the definition of the cables you can see from the table on the right. Okay, so those are the different definitions there. There are 8 different cables in this one. This is a zoom picture for this. So you can see the different definition. We have this 485A, 485B, DI2, DI1, and we have this 24 watts to provide voltage power, and we have DO2, DO1, and the right ones for the grounding. So you can choose. You can see from these definitions of this cable to choose the right endhorse. One thing I would like to mention that the output on the end terminal of CR products is NPN. This tab is NPN, and the input will be PNP, and the rest input and output on the controller cabinet is PNP. So this is a very tricky one, and you need to pay attention to that. So if you are using the PNP, you want to use the PNP type of indicators on the end of the arm, you will need to use a relay to transferring from NPN to PNP. Okay, so in the picture are some models that support our CR robots in the Doobot Plus. So we are developing the interface, the UI user interface for those different models, and lots of RobotTQ robots and the DH robots and Quenway 6 force touch sensors. The packages are all already available in our software. But now we are developing more for more brands and more models in the future. Okay, but if your NTOR is not included, you can try to communicate with the I/O or the RS-485 model bus ITU. Okay. And here is the Doobot Plus. We choose from here, so you can see we have different plugins available. So we have this Sloan-like DH, the force touch sensor, which is from Quenway, the different models like FT300, OnRobot, RobotTQ, 2F85, EPIC, RQ. Also, this is the SafeSkin add-on. So I'd like to mention that if you bought the CR robot with SafeSkin, you also have to install this plugin in the Doobot Plus. Okay, this is the Terminal 9.0 and the weld package. this package is ready to release, and you can use our robot for some wild applications as well. Okay, once the package is installed, and what we need to do first is set the ID and baud rate of the suction cup or the other infectors, and then we choose the baud rate, we choose the ID correctly, and then we initialize it. We are taking the robot TQE peak, for example, in the screenshot, and this is what we do, and this is the interface of it. Okay. After initializing, we can see this user interface here. We can change the different levels, maximum level, minimum level, to give limits to the robot, and also we can choose the arrows to control the robot, to control the grapper manually. So this one grab is to start the electric suction cap release would be released. After the suction cup control interface is configured, we can control the suction cup by using the end tor shortkeys. This is a picture of the end buttons on the robotic arm. You can see we have the different functions here. This is the buttons for the end arms, for the end tors. So what we need to do first is to configure them right in here, and then we can use the buttons to control the robot, to control the end tors and the end of the robotic arm. But now is that end effectors must be adapted. It must be supported by Dubot, and then you can use this button. We will increase more models that we support by this time being. Okay, we will add more models. And those are some API for the effectors, such as this ref epic, which is to initialize it, start it, turn on, turn off the grabber, and so on. So you can also use the APIs in the scripts. Okay, so what do we do usually if we want to use the traditional ways to do the stacking, to do the palletizing? So if we want to move the stack from here to here, so how do we do it? So this is what we do. What we do to write a simple palletizing program. You can see it's quite long, and there will be a lot of moves that is repeating. So first we need to do is initialize the grabber. We need to initialize it, and then we write a function that suck up or reset. Suck up would be for the vacuum to working, and reset means to release. So we write these two functions, and we can call them in the main program. So first we go to the waiting position, and this is the point. P3 is the point aboard the first stack suction position. So then all is ready. We go to it, and then we go RP. RP means the offsite of the P2. First we go to P2, and then we go to offsite. It's about the second stack suction position. So with this, we will go first go to the first points above, and then move to the suction position. We go move and then suck up. This is meaning that we pick up the first we pick up the item, and then we move to up, and then go to the point above, and then move down. So this three is is in 1, and this 3 is 1. And then reset means to release the box to the distance, to the destination. Okay, so and then we repeat one by one, a group here and a group here. This is like a movement like this. We go to here, we go to pick up, move to the next position, and then move down. This is a command just like the jump command. And now this is the traditional way of do palletizing. And now we will have this one. This is what we do. We are using these jump commands that we can easily to call in the program So with the jump command, we can save 3 commands to 1. We can change them to 1. So with these 3, we can all change them to 1 jump commands. You can see that we set up some local parameters. We also the definition of suck up and the release, and then go arc. We set the parameters here, and then we use the jumps. We use the jumps for pickups and place, pick and place. So we are using the jump commands to simplify the program before. You can see what we have in here, we can simplify into here. Okay, you can see this is much easier to understand than what we have in here. Shows us 2 different commands. This is jump 1. And here, the RP means the offset, as I mentioned above, and we can put the parameters the variables in here to definition the pickup pause and place pause and jump, and use the jump commands to do it. Okay. All right. Here's another thing that there will be a Z limit for the jump commands. You can set up for this one if the second point is higher than the Z limit, the jump commands will just go like here, and if the points is below it, it just go regular like here. Okay, if A and B points are just on the Z limit, it will just go as a straight line, just like this one. All right, and there will be a video here, and I'm going to show you here. Okay, this is what we are using for. This is a short demo for the palletizing. Okay, we start, and you can see this is a video for run this script. And here you can see the 2 indicators, the green one and the yellow one. You can see the green one means the movement of the robot, and the yellow one means the running of the scripts. So you can see that the running of the script is always ahead of the robot's move. So this is why we use sync. You can see that the yellow indicator always stops at sync and wait for the green one to reach it. Then they will go together. Okay, this is a simple demo for palletizing. So this is the basic idea of palletizing, is to move from the stack area to the corresponding place area. If you want to do it, there's a simple way of doing it with the process of palletizing. We are working on the current palletizing process, but it's not ready yet. But I can introduce you a little more in advance. So we have 3 different points that we need to use in the palletizing process. That is point A, which is a safety transition point. Point B, which is a preparing point, and target point is point C. Point B is on the high, on the top of usually on the top of point C, but you can also choose to another point. But usually we suggest you to put it right on the target points, just like what we show in the picture. We go to point A, then go to point B, and then placing or picking from point C, and stacking points as well. We go to we move from point C to point B, and then to move point 1. This is a pallet process in our Doobot Studio Pro, and it goes like this. You can find it on the bar here, and you can choose a different XYZ, different layers, different box, how many boxes in different direction, and you can choose the offset in here. Offset you can choose the different C points, prepare points, first point, the same point in there. This function is not very good to use, but we are working on it, and it should be released soon. So if we want to do the stacking process setting, we need to complete the user's coordinate calibration according to the palette, and then set the number and offset in here in each direction, and then complete the positioning teaching. So with this way, we get the robot to know the accurate points, and then it will go to pick up and place. So this is API introduction of processing. First one is palletize matrix here. So we have different values. Those parameter is and stick and user frame is just to change the default mode. It's stacking mode without any specific settings. And this user frame is the serial number of the user coordinate system you use. If it's not set, the default value will be 0. And reset and restore the initializing state. Move in means the robot moves from the current position to the first target point according to the configured stacking path. Move out means the robot moves from the current position to the safe transition point according to the configured stacking path. And extend is to check whether the stacking or unstacking is complete. And release means the release palletizing instance. So we have this this little demo in here you can use for reference. Okay, we will scrap for the demo, and you can check it for you later. And the next thing we will do is for the complex tracking motion learning. As we having this training for 1 hour, so I think we will have a rest for 15 minutes, and we will come back at 20. Okay, I don't know what your time is, and my time is 4 p.m. and 4 minutes. Let's come back at after 50 minutes. Okay, let's have a rest, guys. Okay, see you later.
Nós temos dois por cento. São 2% de artística. Dois por cento. 406. Que era o
All right, everyone, we are back. Okay, the next part of our training today would be the complex tracking motion learning. Okay, to operating the robot to complete complex tracking motion, getting familiar with the use of robotic motion instructions and the COBOL's drag and drop teaching functions, learning the mobilization of the track recorded in script, as well as the use of CR user and Tor coordinates. Those are the objects we are going to learn in this part. So in this part, there will be 3 tests. First one will be complete track motion through motion command. And second, complete track motion through drag and drop teaching. Third one will be the use of user and Tor coordinates. Okay, so here you can see we have 3 different trajectory in here. We have this I don't know how to say it. It's a rectangle, I think. Rectangle. This is the first one with 4 straight lines, and the second would be a triangle. So those are the 2 different simple ways we can do just with go P5 and then prepare a point, then move to P1, and then move P2, P3, P4, and then move back to P1. So with this move, do you remember that the move is a straight line from A to B is a straight line to for move. This is a move command. Okay. So with the move, we can draw something like this, like a rectangle, P1, P2, P3, P4, and then go back to P1. So this makes a triangle, rectangle in here, and then we go back to the prepared position above P1, which is P5. P5 is above P1. P5 in here. So with this simple move, we make a rectangle in here. And the second one would be the let's go to check the triangle first. So the triangle is also very similar to the rectangle. You can see here, we just go to P21. 21 is a point above P22. This is P21. Above here, and then go down to P22, and then move to P23, and then move back to P24, and then move return to the home position of P22, and move up to P21. Okay. Just to easy to understand, and I think this one as well. This is the circle command. So first we go to P17. 17 is a point above P18. This is P17. P17. Then we go to P18, go down to P18, and we use the command circle. Circle 3. We use circle 3 to go to like P19, P20. We move from the current position P18, and then we use these 3 points to go to with P19, P20 to make a circle, and then go back to go P18. This is the circle command, and the 1 here means it goes 1 time, 1 circle. Okay. Here's some videos for you to see how they move. Okay, first we are going to see the score here. This is the rectangle. You see, first P5, then go to P1, 2, 3, 4 more commands. Okay. And then we go triangle. 21, 22, and then move in here. And then the circle, P18, P17 first, and then P18. So in this one, the parameter here is not one. There will be several repeats for this circle. So you can see it's moving around, round, again and again. So that's the difference for this complex motion. Okay. The next part will be the introduction of the end buttons operation. So this is a picture of the end buttons of CR robots. You can see we have this button zooming here. Actually, this photo is a very old one, and now we are changing the colors of these covers on the CR robots. The latest one should be light gray, and so you can see we have these different 5 buttons in here. The biggest one in the center is open or close handhold teach. When the robot is in enabled status, press and hold this button for 2 seconds. You will be ready. You will be able to move the robots freely with your hands. And also, the button on the left is the enable or disable button. So if the payload is configured rightly, you can press the button to enable or disable the robot. When the robot is enabled, you can do with the handhold teach function. Also for this trajectory record button as well. So once the robot is enabled, you can press and hold this button for 2 seconds, and it will start to record the trajectory. And when it's done, press it once, and the trajectory will be recorded. And this button is to playback. When the trajectory is recorded, press and hold this playback button for 2 seconds, and the robot will just repeat what you recorded just now. And the last button here is the control button for the end effectors. As I mentioned in the previous pages, once we configure rightly for the entors, the robot will be able to control the end effectors, such as some suction cups, some grabbers there, just to pick up something. We can control the grabbers with this button as well. Okay. Another thing is that we can see we have different lights. We have different lights in between the buttons. The lights between the buttons shows the status of the robot. Usually, when you just power on the robot, the lights should be green. Should be blue. Sorry, should be steady blue. And when you enable, the lights will turn green. And in trajectory recording, the lights will turn yellow. And there will be a video later. I can show you how the trajectory is recorded. Okay, this is a video, and I can show you. Nope, it's not working. Let's see from here. You see, okay, let's watch the video first. Okay, so from the start, you can see that the lights of the robot is in green. Green means the robot is enabled, which means the powers are now in control of the robot. And in this way, we press the trajectory recording button, and the lights change into yellow. And now we're recording it. You see the moment here? The robot recorded it. Press the button again and press the playback button, and lights will be yellow running, yellow blinking. The robot just repeat what we recorded. Let's watch it again. Record and replay. Okay. This is the end button. Trajectory recording and playing. So you can see with this function, we don't need any computer. We don't need any tablets or smartphones. We can do it with touch of the end buttons. If configured rightly, we can also control the end users, the end effectors on here. Let's continue. So some users might ask, if I recorded some trajectory, how can I call it? How can I use this function in the script or in the blockly? So we developed this function here. We use this rev string. This is the name of the file we just recorded, and we can change it in the settings of the software, and then locate to this, and we start parse this one, and it will do the rest. It will just you can run the scripts to replay your recorded trajectory. Okay, let's check this video. So first, we are going to record the trajectory here. Now it's the same to record the trajectory with the buttons. And now we got this Johnson file. You can see that this is the name. This is the name of the Johnson file. And now we are running the script. You can see the indicators running, and the robot just moved what we recorded. And this is how we use it in the script. We can also do the same in the blockly. We have the block. We have in the latest version of Doobot Studio Pro. We have the block that is you can replay the recorded trajectory. Okay, let's watch it again. First, record it. Then run the script. And now we are running the trajectory. You can see that the trajectory is recorded with the same speed, same time you just recorded. And now it's repeating. Okay. All right. So that is the introduction about the trajectory recording, and now we go back to the next part. Is coordinates. So first one would be the base coordinates. The base coordinate is a coordinate system determined referring to the base of the robotic arm. So you can see here we have this XB, YB, ZB. This is the base coordinates. among which RXB, RYB, and RZB are the rotation angles of the torque center point TCP around the default base coordinate system X, Y, and Z axis, with the Y plus of the base coordinates is constant with the direction of the base loading ahead. Okay, so this is the base coordinate. And now this is the torque coordinate. The default torque coordinate is like this. The torque coordinate system is a coordinate system that defines the position of the TCP, which is the torque center point. Torque center point, which this is the TCP in the center of the flange. Okay. So its origin and direction are constantly changing with the position and angle of the indicators. The current system supports 10 up to 10 torque coordinate systems. Among them, the torque coordinate system 0 represents the default one, which is as shown in the picture. This is the default one. And you can, which is located at the end of the robotic arm. Without no torque installed and cannot be changed. But for the rest of 9, you can change them according to your real needs. And how do we create torque coordinates? In the 6-axis torque coordinate system, you can generate by 3. You can generate the torque coordinates by 3 points teaching methods like TCP and ZX. After installing the torque at the end of the robotic arm, adjust the position of it. And the TCP is aligned to the same point from the 3 different directions, like this, and then the torque position offset is obtained. Then obtain the torque posture offset according to the other 3 points, A, B, and C. And when establishing the torque coordinate system, please ensure that the reference is default torque coordinate system. This is how we establish the torque coordinates. And also here at the system, we can choose from the global coordinates. Users can custom the torque coordinates. There will be 9 torque coordinate systems can be defined by themselves. Users can switch the defined torque coordinate system in the jog interface. Just like this, we can choose the right one. We can create here and choose the right one if you want to use. And this is a user coordinate system. This is a user-defined working bench coordinate system or indictor coordinate system. Its direction of origin and each axis can be determined by actual needs. It's convenient to target the position of each point of the working process and arrange tests. So how do we create user coordinates? Actually, those contents are okay. There are three different ways to do it. The first one is to use dots. We move the NTCP to any points A to determine the origin of the coordinate system and determine the user system direction according to the default torque coordinate system. And we use the line and here to make a straight line by any 2 points A and B. Determine the positive direction of y-axis following the direction from the point A to B. The positive direction of z-axis is determined by the zt-axis to the point A torque coordinate system onto the vertical plane of the straight line, and then determine the positive direction of x-axis according to the right-hand rule. And then the last one will be the plan. According to the 3 points teaching methods, move the manipulator to any move the robot to any 3 points A, B, and C. Among them, point 1, point A is the original and connecting the line between point A, B determines the positive direction of x-axis of the user coordinate system. Point C makes a vertical line along the x-axis to determine the positive direction of y-axis and determines the direction of the z-axis according to the right-hand rule. So with the user coordinates, we can we can do like this. On plan 1, establish a user coordinates, use a 3-point method. On this plan, we establish a coordinate system, and then select several points and write a simple program on to run. Then we move the plan from A to B. We move plan from plan A to plan B, plan 1 to plan 2. And then on plan 2, establish user's coordinates user 2 with a 3-point method, and then change the user coordinates in the program from user 1 to user 2. And then when running the program, the checks of the devices on the 2 plans are constant with each other. So in this way, we can run the same program. We don't have to set up the points again, just use the same coordinates, just using the different coordinates. And here, the next part would be the remote control. So after completing the debugging of the control software of CR robots, select the corresponding remote mode, start, pass, and stop and debug the program through I/O and model bus communication without any need to run the script through the host computer. So during this part, we are going to learn from the remote mode selection, use of remote I/O, IO wiring study, and the use of remote mode bus. So this one first, we have 3 different modes of remote control. The first one would be the software. The software from SC Studio should be changed to Dual Studio Pro. Yeah, this is our previous software, and now we are changing to this one. This is the latest. Okay, so we can change the mode from here. This is online remote I/O, remote mode bus. Okay, this is for the secondary development. And now we are talking about these 3. So we can also control them by remote mode bus and remote I/O. Those are the 3 different ways of remote control. So we have this DI definition for the remote control. DI 11 means to clear alarms, 12 means keep operating, 13 means suspend operation without exciting remote I/O mode, 14 means stop operation and exit remote mode, 15 means enter remote I/O mode and start operation, 16 emergency stop and excite remote I/O mode. And for the DO definitions, DO 13 means ready state, 14 means pass state, 15 means alarm state, 16 means operation state. So we can change, we can check the DO status to know the real state of the robot running. You can also see from here what we have in the software for the different configuration of each DI DO in here. Those are the DI DOs for the remote control. And this is the I/O wiring for CR controller robots. You can see here, CC161 controller is the controller component. And what we need to do to connect the different lines, and you can check them for reference when you use them. This is also included in our user manuals. All right, here is the part of remote bus. So we are using different registers for different functions, so that we can use we can control them by the remote control wire mode bus. For this one, 0x01 is the coil register. Different numbers means different functions. For the 0 means to enter remote mode and start operation. And 1 means suspend operation without exciting remote mode. 2 means operating, 3 means stop operation and excite remote mode. 4 means emergency stop and excite remote mode. 5 means clear alarms. It's much like what we have for the DIDO, and is basically the same way to control it. we use different numbers to represent different functions. And for the 2, 0x02, discrete input register. 0 means auto exit, 1 means ready state, 2 means pass state, 3 means operating state, 4 means alarm state. Then at remote Modbus, the robot is the servo, which is also the slave, and the external equipment is the client as the master. Default IP would be 192.168.5.1, and the port for Modbus remote control would be 502. Okay. For Modbus remote control, we can start up and script running can be done by changing 0x01 for your register status with the help of a Modbus port. But in the latest Modbus, in the latest Doobot Studio Pro, we also have this function, and you can use that inside Doobot Studio Pro. For the same one, the remote Modbus script operating status can be viewed by reading this register 0x02 decrease input register with the help of the Modbus Tor software. Okay, this is the final part of our training today, which is the additional learning tests for the appendix. So in this part, we are going to have this these different topics. First one would be the software information. Second would be the customer's posture. Third one, security settings. Fourth one, hardware installation. Fifth one, software settings. Sixth one, authority management. Seventh one means alarm example. First one, this is a part that we need our users to provide to us when they ask us for support. They need those kind of software versions because there are some a lot of problems are caused by the controller versions or some other versions not matching together. Okay, so what we need to do is to go to settings, basic, and specification. We can know the models in here. We can know the controller version here, 3.5.2.8. We can know the algorithm version here, system version here, and those different versions of the servo, C file, feedback, something like that. We need those versions so to help us to locate the issue. Okay, so with those necessary information, we will be more efficiently to help you to provide our support, our suggestions, our solution to your question. So this is necessary when you need to ask us for help. And this one, users can drag a single joint of the robot by unlocking the joint when the device is not enabled. So this is very important. When the robot, when there's a condition that the robot is not moving and you need to move the robot by the joints, what they need to do is to unlock the brake. Unlock the brake. How do we do it? We go to the settings, find the security setting, and we find the braking here. So you can see we have the 6 brakes for 6 axes. You can just press here just to open the locks. The most important thing is that make sure there's someone by the robot holding it, just in case it falls down when the brakes are unlocked. This is usually used to drag the machine to the apart position through the joints locking. When the robot is enabled in a narrow environment, that may cause hitting of the nearby objects. So please make sure that there's someone nearby, there's someone holding the robot arm, and make sure that the robot will not move in a fast way. Also, you need to make sure that the robot is not enabled, it's in disabled mode. And make sure that someone is near the robot holding it, just in case it falls down by its gravity. And now it's the terminal load. You can see this is the TCP we are talking about. This is the end flange. This is the flange of the CR robots. You can see here. So the torque center of mass offset in CX in X direction, offset CY in Y direction, CZ in Z direction. The unit is NM. So this is the default TCP center. This is it. This is the, you can see here is the buckle here. This is for the end-tor communicating. And this direction, this up down, this up to the up. This way is X and this is Y. And here, this direction is Z. Okay. So this is the offsite payload diagram for each model. So for CR3 here, what does this diagram use to? You can see here, for CR3, we all know that the payload is 3 kg. It's interesting that we name our models with the payload of each one. CR3, 3 kg, CR5, 5 kg, and CR16, 16 kilograms. So this number means the payload it can hold. So for CR3, it's 3 kg. But what do we need this diagram? You know, if we put something right in here, the payload can be 3 kilograms without any problem. But if the NTOR or the loss is too large, for example, if let me use a pen to draw it. So if I use a pen, if I use some TOR like this, which is in a eccentric direction, for example, I'd like to add some TOR in here. And the payload is in here. In this way, there's an offset in the Z direction for like 25 centimeters, and for the XY direction, it should be about 10 centigrams here. So in this way, I will be checking this diagram, and this is the payload that the CR3 now can do with this kind of essential, which is 1 kilograms. Which means if I use a TOR like this, the payload would be different. It would be less than 3 kilograms. The TOR is in here, and the payload will be less than 3 kg. It turns to 1 kg. So if you want to calculate the payload of your object, you must measure the offset in each direction of your NTORs. And it's all the same for the rest of them. CR5, also I will draw another one. For example, if your grapper or something is like this long, and in this way, you want to pick up something in this direction with offset in XY in like 18 centimeter and Z 25 centimeter. The payload of your robot will decrease into 2 kilograms in here. That's where you should check. Okay. So those diagrams for different models is for your reference when you want to do something very offset to the TCP points. You need to use this diagram to calculate how much value, how much load you can put on the end arm. And this is CR10 as well. For this range, is 10 kilograms without any problem. This one, this one, 8. And for this one, 6. So the longer the tour you have, the less value, the less payload you can hold with your CR robots. It's all the same for 16. Just that the offside is much longer and than the others. Okay, once we have settled the offset in XYZ directions, we will use those parameters to tap in when enable the robot. We need to enter the offset in each direction here when you enable it, and we will input the value into it, and so the robot will calculate by itself to see how much force it should output. And here, we just mentioned that we can use the buttons to make the robot into teach mode. And if you have trouble, you find it very difficult to drag. If you have you have done something like this, you can change the sensitivity of each joints to make it much smoother or much harder to move. You can change it here in the settings to change the sensitivity of each joints. All right. In addition to the conventional installation, CR robots also support left and side installation, and the rotation angle and the installation angle need to be set with different installation methods, and you can choose one here. You can choose the right direction you want to install. Users can get installed in rotation angle and tilt angle through the interface collaboration function. Adjust the robot position by inching and making the terminal flange face up and particularly to the ground. Then click collaboration button. And during the conventional installation of the machine, the rotation angle and the installation angle are both set to 0. Otherwise, there will be error during it. Do not modify it. Another thing is that we can change the IP of the line port of the controller by in the settings of the software. Only the IP address of LAN 2. Notice that there are 2 LAN ports for the MG400, and the only LAN 2 can be modified, and you can choose your own IP address in here. The default one would be 192.168.51 by the cable for CR robots, and 1.6 by Wi-Fi. So when you change the IP address, these two are reserved ID IP addresses, and you cannot use them. Other than those 2, you can use them to change your modified IP. Also, each CR robot comes with a Wi-Fi module, which is a Wi-Fi adapter, and the default name of the Wi-Fi would be the SN number of the robot, and you can also change the Wi-Fi's name and password in the settings here. You can change to anything you like here. But usually we don't suggest our users to change it, because in default there will be the SN, so that you can know which is the model, which is the robot you are connecting to. Okay, so that's it. So here is some alarm introduction that we we like to introduce you might be encountered during your usage. So we have this positive limit alarm. It means when the joint jogging exceeds the set range and the limit alarm will be reported. What we need to do is to jog the joints towards the opposite direction, and then the problem will be solved. For example, we have this positive limit of joint 6. What we need to do, like this, we need to, it's reaching 360 degrees. What we need to do is press minus so that this value can go to the negative direction so that the positive limit will be cleared. It's all the same for the other negative limit alarm. Another thing is that, which is common for the collaborative robot, is the singularity alarm. So you can see that we have different types of singularity grams. The joint, the TCP of the robot is located in the plane, which is composed of G1 axis and G2 axis, which will lead to the singularity. Singular position of elbow joint is when the robot is when the bottom and the forearm of the robot are in a straight line. It will lead to it. And also we have this west joint singularity position. When J4 and J6 axis of the robot are in the parallels, it will result in the singularity. We have some photos for you that you can check for reference. This is the shoulder singularity point. You can see the TCP here. The TCP here is located in the plane performed by the joint 1, joint 2. We have joint 1 here, joint 2 here. Those two joints, those two lines, center of joint 1 and center of joint 2 makes up a plane, and the center TCP is located in this plane. This is a singularity point, which is called shoulder singularity. And second one is elbow singularity, which means the rear arm and the forearm are in the straight line. This is the forearm, this is the rear arm, and now you can see they are in a straight line. This is the elbow singularity. The last one is the rest singularity. You can see that joint 6 and joint 4. So the center line of two joints are alleged they are parallel to each other. This is also the rest singularity. So for these 3 different conditions is what we should avoid. This will cause the singularity alarm, and the robot will behave in an unexpected way. So this is what we should do. What we should do to avoid this. We need to, when the error happens, we need to choose some other points to avoid this posture happen. And this is an API parameter error. When the API is programmed incorrectly in the script, this kind of error will appear. This is called controller error, and the Go command has no input parameters. You need to go back to check your scripts to see if there's some parameter missing or some other contents missing. And here, alarming. When the script is wrong, the parent window will also promote the specific location of that error, which is commanded for us to target the error. You can see here we have this alarming here. Attempts to call a null value in here. This one we will guide you to locate the issue. Okay, this is the 4 content of our training today. And if you have any question, feel free to ask us here. You can type in the chat box here, or you can just send email to us, or you can just send a voice to us. Okay.